My name is Amir Trabelsi. I'm the CEO of Genox. I want to thank Bionano for the invitation. I'm happy to be here and talk. There are three things you need to know about me before we start. First, I'm not a scientist. I'm not a biologist. I'm not a clinician. So the presentation may be less scientific. I'm a data guy, data analytics and cybersecurity, to be more specific. I'm originally from Israel, even though now I live in the Bay Area. And third, people from Israel do tend to pronounce words with the letter R in a funny way. So you may want to excuse me for that. So today I'm going to talk with you a bit about Genox, about the company, about artificial intelligence. What did we tell you? What do they tell you? What do they not? How we see artificial intelligence specifically in structural variant interpretation, but overall in genetic data analysis. And I will end with some summary and questions if you may have. So a bit about the company. I hope you see it. We were founded in 2014. We're deployed in more than 70 centers. We're a team of genetic and AI experts. And we are focused on data analysis. And of course, using a validated adaptive AI in our solutions. I want to talk a little bit about our solution. In general, we have three solutions, one for interpretation and reporting. This is what I will mainly focus today. The other one is about population studies, where you can take all your patients' data and find patterns and correlation across a variety of different cohorts of patients, different studies, different phenotypic data all together. And the third is more of a data sharing and management, where you can manage your patient data, how to share the insights with part of the organization, how to ensure compliance between different sides of the organization. But as I mentioned, I'm going to focus mainly on the first solution for today. So before we will jump to AI, there is a moment or a time where you realize or you recognize the value of computers. I picked this one as, and I hope you see it properly, it's Jerry Kasparov beaten by Deep Blue in chess game in '96. This is where I think where the recognition of machine learning or machine versus human in general got into the public. And today I think artificial intelligence is like everywhere. You see it in the literature, in publication. It's had like more than 20,000 mentioned already all over. You see it in job seeking. You see it pretty much everywhere. And in fact, I think that the reality and what they promise us that eventually the machine will replace the human and will do everything for us, and we will have now a lot of available time. It's not the reality. And the reality is actually this. I'm sure that you're still loaded with data, with figures, with elements that you still need to analyze by hand. You still need to go over it. And in fact, we have less time to go over things. And perhaps this is the time to kind of stop for a second and think about AI as a definition. That definition, and I checked it in Google, and obviously it's biased, but the definition for AI is how can a systematic approach of machine can replace a human work. And if you think about it, it's actually outline it human versus machine. But if we will think about artificial intelligence as tools that can help us to make the work more effectively, and this is why I like the phrase intelligence augmentation, where it's enhanced our ability just to do our work better. This is where the value of AI actually comes. It's a set of tools, sets of very specific problems that can be solved using machines, and that all together can increase our productivity, can be more efficient and more effective. And as you will see, I will discuss about it in a few examples that I'm going to show. So you kind of see the next slide already, but what's important in this slide is those two is those two figures. So a study that was done and published in New England Journal of Medicine took two cohorts, and they performed a reanalysis over. One cohort was 250 patients, the other one was 2,000 patients, and they were able to increase the diagnosis yield dramatically, even though it's in old cases, and they were taken from 2012 to 2017, so it's kind of a 5 years. So of course that the diagnosis yield will be improved, but still going deeper into what they've analyzed and what's increased the diagnosis rate, we see that a CNV detection, new evidences, variant classification, of course, misdiagnosis, as we always see in some of the diagnoses, and all of them help to systematically improve the diagnosis yield. The diagnosis yield. Now, if we can do it in a systematic way, and I think this is where AI and artificial intelligence tools can really be helpful, is to perform those systematic review of the information, highlight information that we may have missed if we didn't look through those tools. And I'm going to give specific example for that. And so let's try first with the title and then without. So how we can turn artificial intelligence into augmented intelligence. And I took 3 different examples, as I'm going to illustrate soon with few examples from the system. A classic way is noise reduction. We know today that most of the variant calling use some sort of AI in their core, or machine learning, or some statistical approaches in order to reduce noises in the calling, in order to provide us the most accurate variants that detected in the sample. And AI is obviously a classic way to solve some problems. I'm going to discuss how we can improve today's structural variants using optical mapping and next-generation sequencing in order to reduce noises from both signals. Automation and prioritization. We have today a lot of signals, a lot of data that we get. So even if we have the variant itself, we still have a family history, we still have the phenotypic of the patient, we still have many literature that we want to perhaps mine and see if something is related to what we're doing. And if we can get all the signals together, ranked and prioritized by the order of the priority to what matter to us, it's something that can help us in order to do our work more effectively. And third, I didn't find any other good name for it, so I just put it as connecting the dots. But in many areas, you have some blind spots. And think of an example of you have a combination of SNPs and structural variants together. You have a compound heterozygote. You have many things that with the right prioritization injected in the right visualization, you can pretty much see it just in front of you that otherwise you could have been missed. And with that, I do want to go to the examples. So this is going to be a bit tricky.
Can you scroll with the...
Yeah, that's what I'm trying to do now. Yeah, OK, perfect. So we see here a sample that we got from an NGS, and we see that the short reads kind of reveal that there is something here, but it's not accurately defined because the short signals are too noisy to detect the structural variants. We also know that there is a deletion that we got from the Bionano, the optical mapping, and this is another signal that we got into it. But we don't know precisely where to put the structural variants because the uncertainty of the breaking points are in the few thousand of base pairs. But what if we can take the short reads, we can prioritize them through a ranking system that we have developed according to their confidence, get the signals from the Bionano, and realign it together with the signals from the Bionano using a graph alignment approach, and be able to align those reads specifically on the points themselves. What's this approach of taking the short reads, prioritize them, remove what is not contributing to the signal, merge them with the optical mapping signal, allow us to refine the breaking points from a few thousand of base pairs to something around 12 base pairs. And we do it today for insertion, for deletion. We're soon doing it for translocation and inversion as well. And with that information, we can continue in the upstream and doing the interpretation itself. But before I will jump to the interpretation side of it, how do we do it in fact? We have the NGS data and we have the optical mapping data. We then go into 2 different separated mode of works. One is to do the variant calling for the NGS. And then we start to prioritize all the areas that are marked by Bionano signals as potential structural variants. We take those reads, realign them using our graph alignment and using our ranking of the reads, and we are able to get those more precise deletions, insertion, and soon translocations and inversions. We validated the results on one of the GEP samples, as you can see here. In total, we could see that for deletions, we refined the breakpoints to a range of something between 8 base pairs to 12 base pairs. And for insertion, it was something between 22 base pairs to 140 base pairs. And in order to show the specificity of this approach, we also simulated false signals. So not getting only the signals that are true structural variants, and we were able to get to 98% specificity for deletions and for 90% for insertion. And all of this approach now take us to the interpretation and how to use this information in the upstream analysis in order to actually detect what we're looking for. So this is the same sample, the same 56 base pair deletion that we have found. You can see here that if I will open all the details of it, I can see that it's very rare in the population because we looked at TGV, we looked at 1,000 genome, we look at the exact, we look at GNOMAD as well. We can learn further about the confidence of those breaking points just by looking into further information that we provide on that. And we can see that this specific gene perfectly matched our case phenotype. We put the case phenotype here, and you see that the Miles-Carpenter syndrome is ranked in 71% correlation to those phenotype. And how we are doing those genotype to phenotype ranking, we have another module that uses machine learning approaches that went over phenotypic data and sample data, and were able to rank those correlations. I talked about automation and how you can make the prioritization of all the data that you get in a more proper way. Because today, if you think about it, you have the signals and you have the noises that you get from the variant calling. You have the family history, you have the phenotypic data of the patient, you have the literature mining, you have a lot of evidences that you may want to include in your analysis. And this is, again, a real case that we have in the system. And you can see here that currently there is no data in it, but if I will click to the next slide, I've just uploaded the family history. The father and the mother are healthy. The child is affected. We have added the phenotypic data here in order to analyze all the data together. And what's the results of this all signals together will provide us 3 variants. One of them is structural variants, and 2 other are SNP. So we combined all the SNP, all the structural variants together. We prioritize them for you, so you can now review those 3. Now, it may not be relevant to your case. It may be relevant to your case. You can still continue and explore all the variants in the case. But let's take, for example, those 3. I can see, I'm not sure if it will work, but you can see here there is a tiny bar. And this bar actually reflects the gene to phenotype ranking that I've showed you again. So you see that the 2 others are very low on the ranking itself, and the first one is very high, and it also has some clinical evidence to it. And again, the first is a structural variant that was combined with the NGS data, so it's allow us to find both of them on the same screen. And if I want to now read more about this specific gene and about the KISS phenotype, what was matched, what was not matched, I can see that the ranking is 83%. I can see that it's the most relevant disease was Rubinstein-Taybi syndrome. This is the confirmed eventually disease for this specific patient. And I can explore more. I can say I don't trust the ranking itself, and I want to see more publications about this specific gene. So we show you all the relevant evidences that we picked, of course, prioritized by the relevance. And you can scroll down and you can see all of them and more information if you want to confirm this assessment. You can even open a viewer where you can see this deletion and you can see all the curated submissions of structural variants that were taken from different public databases, even yourself, even if you want to inject your own internal repository of structural variants that you already curated. So we see that our classification classified the variants on top, the deletion, as a likely pathogenic variant, but we can also see that there is some curated submissions for pathogenic variants. There is also many pathogenic SNP variants across this region that may increase our confidence that this is indeed a likely pathogenic variant. And as I mentioned, it's not end here. It's pretty much you have control to go over the SNPs, to go over the CNVs together. If you don't want to use this prioritization, you still be able to deep dive into all the results themselves, filter them using variety of filter options, and conclude your assessment with it. The third case, it's kind of a tricky case because in many of the cases we may miss those scenarios. But if we're taking what I've mentioned about the prioritization, prioritize the variants that are most relevant to the case phenotype. If I'm taking the classification itself, measure how pathogenic those variants are. And if I'm taking cases like this, where you can see that you have, in this specific case, it's two healthy parents that were actually screened for carrier screening, but their child came up with hearing loss and hearing problems. And the reason, eventually, when they screen it, they found deletions that identified in GJB6 and CRLY genes. But in addition, there was also a SNP, a pathogenic SNP that was on GJB2. And combining together, that was aligned to the case phenotype. Now, otherwise, if we looked at it and we looked at it without the prioritization of those variants on top, it was, I don't say that it wasn't possible to find it. It was just very hard, time-consuming. And eventually, I think this is the most powerful value of artificial intelligence as we see it. It helps you to do the work eventually more effectively, reduce the time that you need to go over evidences, literature, and prioritize all your data accordingly. So just perhaps to summarize, I'll try to use the title. So it's not a black box, and this is perhaps the main message that I want you to take from here. AI is not necessarily a black box. It can be a black box where you just get a result, but it's not necessarily a black box. It can be just an effective way to improve your workflows and to enhance your work. Our specific classification and prioritization engine complies with the clinical guidelines. We did a validation study specifically for the ASMG and AMP guidelines. We are also taking into consideration different genes approaches. So we're not just doing a generic threshold. We learn from each gene what are the right thresholds in order to prioritize the results accurately. The genotype to phenotype ranking, we incorporate the case phenotype in order to prioritize all the variants together. And we take, of course, other scenarios such as the inheritance model of the families and compound variants. Just a bit about the validation that we did to the classification and the prioritization engine. We took CleanVar data for a specific time. We took it 12 months prior to that. And then we tried to predict the results on 12 months ahead. Of course, removing all the evidences referring to CleanVar. And we get a very high classification accuracy of almost 99% of all the cases. And the turnover of this all over for a genome is less than 15 minutes. in order to validate our gene-specific approaches, what we did, is we took specific gene panel experts that some of the clean groups are working with, and we tested for each criteria differently. And in this example, I have only the two of them, PM1 and PS2. So we show a high concordance between the expert panel group results and our classification. What we basically did, we predicted what would be the threshold that will be recommended by the expert groups for specifically in those rules were for frequency for benign, frequency for pathogenic, and we saw that there is a high concordance for our recommendation for the gene frequencies and our classification engine. There are 4 different studies that we did on it. All of them are available online on our website. So it's just on the genox.com publication. We did different validation for both frequencies, for the hotspot regions, for the weight of PM1 rules, for the loss of functions, and of course to the frequencies themselves. And that's it. We are at booth 504. We're happy to give a full demonstration of some of the capabilities we mentioned. There is also a free tool online called Franklin that use all those classification. You can use it for free. It's just franklin.genox.com. So if you will go, or if you will go to our website, you will see it. You will see a link to it, and you can just browse it, use it for classification. It gives all the information, including text mining, publication, structural variants, classification, and everything that I showed here. Very nice and intuitive tool. And of course, you can also manage all your variants from it and get updates if anything in the literature or in the evidences changes. So with that, I'll end, and I want to thank you everyone for listening.